The corticospinal tract represents the highest order of motor function in humans and is most directly involved in control of fine digital movement, such as flexion of our pinky. In this video, we will be exploring how the brain signals to the muscles to contract. We will look at the cortical structures involved and how the signal in the form of an action potential propagates down the corticospinal tract before reaching and synapsing on the muscle at the motor end plates. To aid in this explanation, we will be exploring this pathway through Alberto the Action Potential's epic journey. The corticospinal tract begins at the cortex of the brain, specifically in the precentral gyrus known as the primary motor cortex. This region is located just anterior to the central sulcus. The cortex is comprised of grey matter, which is divided into 6 layers based on the cytoarchitecture. Deep to the grey matter is the white matter, which is predominantly comprised of neuronal axons. In the precentral gyrus, layer 5 is the most prominent and is responsible for sending motor information to the periphery. Located within this layer are large pyramidal upper motor neurons, known as Bett cells. These cells are multipolar neurons of the CNS with myelinated axons that project to form the origin of the corticospinal tract. The axons of Bett cells enter the white matter just below layer 6. As these axons proceed deeper into the brain, the small bundles of white matter combine to form the corona radiata. The axons continue to descend deeper, and, at this point, form part of the internal capsule. This is found between the lentiform nucleus, caudate nucleus, and the thalamus, and carries information past the basal ganglia until it reaches the brainstem. On a dark night in the middle of Cortex City, while everyone is asleep, our brave hero meets Betty the Bett cell. "Alberto, this mission is very important," whispers Betty. "You must take this message and deliver it to Mr. Pinky. Follow my axon until you can go no further. I can't help you after that." Travelling inferiorly, the Bett cell axon enters the brainstem via the ipsilateral cerebral peduncle, continuous with the internal capsule in the rostral midbrain. The white matter fibre bundle travels ventrally through the length of the brainstem via the midbrain, pons, and medulla. At the level of the pons, an axon collateral leaves the corticospinal tract to synapse with the pontine nuclei. The pontocerebellar fibres projecting from these nuclei travel through the middle cerebellar peduncle into the neocerebellar cortex. This information allows for fine adjustment of motor movement through communications with the motor cortex of the cerebrum. The axon continues travelling inferiorly in the ventral portion of the medulla. Here, the fibre bundles are visible externally and known as the pyramids. Just below the pyramids, 75 to 90% of the fibres decussate to the contralateral side of the closed medulla, forming the lateral corticospinal tract. The remaining fibres form the anterior portion of the corticospinal tract. Along his journey, Alberto passes the great pyramids of medulla. The vast open spaces of the medulla begin to close. Our faithful traveller crosses to the other side. Remaining contralateral, the majority of the corticospinal tract now descends past the foramen magnum in the most lateral white matter portion of the spinal cord, the lateral funiculus. The Bett cell axon continues until it reaches the level of C8 in the spinal cord, between C7 and T1 vertebrae. At this point, it terminates on the ventral horn, synapsing onto a multipolar lower motor neuron, in this case, an alpha motor neuron. Alberto reaches the end of Bett cell Road and says goodbye to his dear friend. Oh, what will he do now? "Bonjour, monsieur," exclaims Louis the lower motor neuron. "I will take you from here." The axon of the lower motor neuron leaves the anterior horn, forming anterior rootlets. Multiple anterior rootlets arise from the spinal cord to form a single ventral root. These roots contain motor axons. The dorsal root contains sensory information which will travel back to the brain. Each dorsal root and ventral root then unite within the intervertebral foramen to become a spinal nerve. After leaving the intervertebral foramen, the spinal nerve typically splits into several branches, which are termed rami. The anterior ramus innervates the anterior and lateral portions of the trunk. C5 to T1 spinal nerves form part of the brachial plexus. The brachial plexus is a network of nerves that supply the upper limbs. The components of the brachial plexus extend laterally from the neck. The ulnar nerve arises from the medial cord and descends along the medial side of the arm. The rolling fields of brachial plexus, the land of roads dividing. Alberto feels confident that he will take the right turns. He holds tightly onto the scroll in his hand. These trusty directions have not failed him yet. The ulnar nerve has no innervation in the upper arm. At the elbow, the ulnar nerve continues through the epicondylar groove, which is formed by the medial epicondyle of the humerus and the olecranon process of the ulna. Oh no! Ahead lies the most dangerous part of Alberto's journey. Once he summits this treacherous mountain, he arrives at the most exposed and prone to injury point in all of Bodyland. There is nothing funny about this, Alberto whimpers. The ulnar nerve innervates muscles in the medial forearm, as well as intrinsic hand muscles, including the flexor digiti minimi brevis. Upon receiving impulses from the lower motor neuron, this muscle, via the ulnar nerve, causes flexion of the pinky. Hooray! Alberto has delivered the message from Cortex City to Mr. Pinky's men. These men work tirelessly to follow the orders received. But what happens next will blow your mind.